So, today we're going to talk about end behavior and zeros of rational functions. So, a rational function is the quotient of two polynomials. Or it could be a monomial there as well. What does that word quotient mean? It's division. Which can be presented as a fraction, right? So, examples of rational functions, you could have something like 2 over x plus 3. You could have x squared minus 3x plus 1 over 3x plus 4. You could have, they can just get as complicated as you want. Something to watch out for, like if I have y equals x squared plus 3x over 4, is that a rational function? It is not. What makes that different? No, x is in the bottom. Okay, so this would not be considered, this is not rational because no x's in the denominator. This could be written as y equals 1/4 times x squared plus 3x. This will just be a quadratic right here. So if you don't have an x in the bottom, then it's not a rational function, even though it sometimes looks like it is.
But you don't have to have like an x on the top, right?
Right. You do not have to have x in the top. So like you could have f of x equals 1 over x. That would still be rational there. As long as there is some x in the bottom. If you start putting things like square root of x in the bottom, I guess that would still be rational, but it's a more complicated version and not really what we're talking about here. So it's going to be like a polynomial that we'll see here. All right, so let's talk about the most simple that I just put up there of all rational functions, which is just f of x equals 1 over x. So if we're thinking about the end behavior of 1 over x, if we're looking at the limit as x approaches negative infinity of f of x, this would be that left side, right? And we're thinking about what happens on the left side of this function. If I sort of make myself a table that is approaching negative infinity, so I'm putting in numbers that are lower and lower and lower, then I can get an idea of what is happening. So first I would have I'd have 1 over negative 1, which would just be negative 1. And then when I plug in negative 2, I would get negative 1/2. Negative 5 would give me negative 1/5. Then I got negative 1/10, negative 1 over 100, negative 1 over 1,000.
You're just plugging those in to the x.
Yep, just plugging in for x right there. What's happening to those numbers? They're getting smaller and smaller and smaller and smaller. We're getting, like if we were doing decimals here, we're getting tinier and tinier and tinier decimals, right? What are we getting closer to? We're getting closer to 0, right? So think of it like a pizza. You have a pizza. I mean, we're in negatives now, which makes it not really make much sense. But if we do the positives, we got 1 over 1. We got 1/2. We got 1 over 5. We got 1 over 10. We got 1 over 100. We got 1 over 1,000. Think of having a pizza for a party. If you have a pizza for a party and nobody shows up to your party and it's just you, you get to eat the whole pizza, right? You get one whole pizza. But if 2 people are there, you each get half of a pizza. If 5 people show up, you get a fifth of a pizza. If you have 10 or 100 or 1,000, you're just like, if you have 1,000 people at your pizza party and you only bought one pizza, everybody gets 1/1,000th of a pizza. A piece of pizza, right? So it will not be the best pizza party they have ever had in their life, for sure. So you're just getting closer and closer and closer to 0. And it doesn't really matter whether it's negative or positive. the decimals are getting so tiny that you're just approaching 0. So on just regular polynomial functions, when we did left and right end behavior, we always had positive or negative infinity, right? Because those types of functions always go up forever or down forever, not rationals, okay? So we're going to get 0 for both of these limits, both for the left side and for the right side. Okay, so rational functions often have what we call a horizontal asymptote. So rather than going up forever or down forever, they sort of level out at a number there. So, moving on, here is one that is a little bit more complicated. And because this one is a little bit more complicated, I'm going to go out of the slideshow so that we can, let me do the presenter view. Right now, I'm going to let you use the calculator. We will learn something in a minute that will make it not necessary to have the calculator. But certainly right now, while we're kind of exploring, I really don't want to plug in negative 1,000 into this. Although I could. Should I? I might should. Let's do the positives without the calculator. Okay, just because I want you to see what's happening, right? Okay, so like, if I'm doing the positives, if I'm doing 1, oh, well, let me do the pen from this view. Let's see. Okay, if I'm doing 1 squared plus 2 times 1 over 1 cubed, then that is going to be 1 plus 2, which will give me 3 over 1. So I get 3 right here. If I do 10 squared plus 2 times 10 over 10 to the third, that is going to give me 100 plus 20 over 1,000. Right, so 120 over 1,000. When we divide something by 1,000, we move the decimal 3 places to the left, so we'll get like 0.12 here.
You wouldn't leave it as a fraction. It would be a decimal.
You could do either one. You could do either one. And then for 100, we got 100 squared plus 2 times 100 over 100 squared. So we will get, cubed. So we will get 100 squared is going to be 100 times 100, which will have 4 zeros with it. So we got 10,000 plus 200 over 100 cubed is going to be 100 times 100 times 100. So it will have 6 zeros. So we'll get 1, 2, 3, 4, 5, 6. We'll get 1,000,000 on the bottom. Now, that gives me, oh gracious, we got 10200 over 1,000,000. 2, 3, 4, 5, 6. I'm running out of room bad on this one. We'll do the last one with the calculator. So I got to move my decimals 6 places this time. So I got 1, 2, 3, 4, 5, 6. And I've got 0.0102. And then if I do 1,000, let's skip over here to where we're using the calculator now for 1,000. Oh gosh, that really is awful looking, isn't it? So if I do 1,000 to the second, I'm going to do it piece by piece, just so you guys can see. Then you'll have 2 times 1,000, and then you'll have 1,000 to the third. So that will be, so that's got 6 zeros, plus 2,000. And then this is going to be 9 zeros. Okay, so I get 0.001002. So when we're doing that, all of the numbers are getting a lot bigger, right? But which number is getting the biggest fastest? It's going to be that bottom number, right? So we're going to see this happening throughout, right? So this, as you can see, what are we approaching here? We're approaching 0 on this one. If we look at the negatives, that I'm going to just use the calculator in a more efficient way. Also, I did not notice, but I have a typo right here. I called this H, and then I'm using F right here, which is not right. Let's make that H there. I meant to change that, and I didn't. So if I've got H of X equals X squared plus 2X over X to the third, if I do H of negative 1. Actually, I probably should just change that to F because my table also has F's here. That's really H right there. Yeah. Well, next one we'll just change to F's. I copied and pasted that. Slide and changed this, but shouldn't have. All right. So H of negative 1 gives me 1. H of negative 10 gives me negative 0.08. H of negative 100 gives me negative 0.0098. And if I add one more 0 and do 1,000, I get negative 0.000998. So what do I approach here as well? I'm getting closer and closer and closer to 0 because that's, even though it's coming from the negative side, it is still just getting tiny, 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 right?
So like even though you start at 1 and then go negative, you're still approaching 0?
Mm-hmm. Yeah, because when you're looking at end behavior, you're only talking about like what's happening way out at the ends of the graph. So you're wanting to see what happens as the numbers get really big. So sometimes they'll do crazy stuff when you start plugging in smaller numbers, but as you go out to the ends of the graph, it's going to, have a trend. Yes. We will find out. Good question to ask yourself right now. We're going to find out. It seems like 0 is happening a lot. But let's look at this one. So for this one, I've done the same thing here. Let's just change this to an F this time. I've got F of X equals 100 minus X squared over X. So we'll do this. All right, so here's a good thing to know on Desmos if you do not know how to make a table on Desmos, because I don't know if we've done it. I think you know how to like add a table and put numbers into the table. I don't know if you know how to make a table for a function. So if you put the plus sign and you hit table right here, then you can do x1 will be automatically what you have here. This used to say y1, so I made it f of x1. Okay. So if I plug in negative 1, it'll calculate it for me. And then I could do negative 100 and, negative 10 and negative 100 and negative 1,000. Now let's look at what's happening here. Now I've got negative 99, 0, 99, 999.99. Now, this one does not look like it's going to 0. It looks like it's going up. And if you're not sure, you could just like keep, oops, wrong thing. You could just keep going. Negative 10,000, negative. Yeah. Oh, yeah. It's definitely just going up a bunch, right? So this on the left side approaches positive infinity. On the right side, we would need positive numbers. So we do 1, 10, 100, 1,000. Okay. Notice here we got 99, 0, negative 99, negative 999.99. What are we approaching on the right side? Negative infinity.
So is it just like this specific problem, or are they always like kind of opposite to each other?
Just a specific problem. They could match. Like they could be anything.
Okay.
Yeah. Depending on what they've given you for the problem. Okay. So end behavior. Let's look at the end behavior, because this is not always on calculator active. So you can't always plug numbers into a table like we just did. So the end behavior of a rational function is dominated by the term with the highest degree, or the largest exponent. Okay? So the first thing you want to look at is if the term with the highest degree is in the blank as the x values decrease or increase without bound, the y values will approach blank. Okay, yeah. In the denominator. Okay, so if your highest degree is in the denominator, your y values will approach 0. Okay, this happens because if we think about this one over here, when I specifically wanted to do just a little bit of this by hand, so you're looking at what the numbers do. All those numbers were getting a lot bigger. But, like, for that last one, my bottom is getting bigger much faster because I'm raising it to the third power, right? Especially the 2x starts to really not matter at all. Like, this 200 is very small compared to how big the other numbers have gotten. But the higher the exponent, the faster that is going to grow, and it's going to be the only thing that matters after a little while. So, whenever I look at a problem like this right here, I don't have to make a table. I can just see, oh, this has the biggest exponent right here in the bottom of the fraction. So the limit on either end is going to approach 0. Okay, so we can do these very quickly whenever we see it. Now let's look at our other one here. If the highest exponent is in the numerator, okay, as the x values increase or decrease without bound, the y values will approach either positive infinity or negative infinity. Should I be doing my? I guess I should. All right, let's back up. I've got a saying to help us remember things with this. Did you guys do, for horizontal asymptotes last year, did you guys do Bobo-Botno eats DC? All right, so Bobo-Botno kind of applies here, okay? So, Bobo-Botno, of course, is not going to be a mathematical reason that you can put on the AP exam. Do not answer a question and put the limit as x approaches negative infinity of f of x equals 0 because of Bobo-Botno. That's not going to get you credit. This is just something to help you remember. So, this one right here, so if you go back to the one where it equals 0, this is Bobo. And it stands for bigger on bottom. The last O is 0. Okay, so this lets me. So bigger on bottom 0. That is your bobo part. So if you have the exponent is bigger on the bottom, then you will get 0 for that. Okay? This next part. Okay? If the highest exponent is in the numerator, as the x and y values decrease without bound, the y values will approach either positive or negative infinity. This is Botno. That stands for bigger on top, not 1. I think that the teacher, I don't know what teacher came up with this. I learned this in high school. Whenever I came here, like a lot of the other, like Coach Wood definitely knew it. I don't know if everybody around here went to some training where they learned about Bobo Botno HCC sometime. It's definitely not in any, like, textbooks or anything, but it is helpful. So, not 1, it's really written for horizontal asymptotes. So, it means there's, not 1 means no horizontal asymptote, which also means that since you're not approaching a number, you're either going to be going to positive or negative infinity. So when you're thinking about limits, we can also think it means there's not a limit, because you can say that a limit equals infinity, but you could also say that those limits do not exist. Like if we were in calculus, we'd talk about it a little bit more. Because if you were riding down the road and you saw a speed limit sign that said speed limit infinity, is there a speed limit? There is no speed limit, right? It's not really a limit, because a limit would imply it's a stopping point, right, that you have to go to. So technically, whenever you have limits that equal infinity, you can write it. It's okay to put it, but they don't really exist. They're not.
So it's not a limit?
Yeah, it's not a limit for that. So whenever we have bigger on top, not 1, it means there's no horizontal asymptote, or you can think of it as not a limit, but it can be positive infinity or negative infinity is what you're usually going to answer it with. So you have to think a little harder on finding end behavior for this. Okay, so we got this like complicated looking thing here. It says if f of x equals ax to the n over bx to the d, then f has the end behavior of the polynomial function given by y equals a over bx to the n minus d. Okay, let me give you, actually, do I have it on the next slide? Or yeah, we'll look at it on the next slide. I'll give you an example of, well, no, let me do one here. I think that'll be better. So, like, for example, let's say we were doing the end behavior of f of x equals 3x to the 4th minus 7x squared over negative 2x squared plus 1. So when you are doing this here, so let me change my color. There we go. When we are doing this here, when you're doing end behavior, you're looking out way at the ends of the graph, right? So only the highest terms matter. Only the highest terms affect what's going on here. So because when the numbers get really big, this plus 1 over here is so tiny it doesn't change much, right? It doesn't affect a lot at all. Over here, this is going to matter a little bit more. The one that really matters the most is that x to the 4th on top. So what you're going to do to determine end behavior is you are going to take the 3x to the 4th over negative 2x squared, and you're going to reduce it. Okay? So if 3 over negative 2 would reduce, you would reduce it. It does not. You're going to get negative 3 halves. And then you've got x to the 4th over x squared. So that means you've got 4x's on the top, and you've got 2x's on the bottom, and those x's can cancel, and it's just going to give you x squared. Okay, so you want to think of what the end behavior of this would be. Okay, we will get negative infinity on the right side for sure. What about the left side? Also negative infinity, right? Because we got a negative coefficient there, so that tells me that the limit as x approaches infinity of f of x is going to equal negative infinity. And because you have an even exponent, and you're not looking at these, you're looking at your reduced version of it, you'll have the limit as x approaches negative infinity of f of x will also equal negative infinity. Okay, let's do a couple more. Okay, so if I look at these, right, they are all bigger on top. Do you guys agree? Highest exponent is bigger on all of them, on the top. So these are all going to be either positive or negative infinity. So what I'm going to do is I'm going to take my highest degree from the top, my highest degree from the bottom. Right? I divide them, which would give me 1x squared over 3x. And that will be 1/3 x to the first power. And then I'm going to look at end behavior of 1/3 x to the first power. So always do your right side first. You have a positive coefficient, so you're going to get positive infinity here. I have an odd degree, which tells me they go in opposite directions. So I'll get negative infinity here. Does that make sense? Try the next two on your own. All right, check with your buddy and see what they got. See if they've got it. Write it either in the top or you can put it like over to the side, but it doesn't go like both places for that. Because whenever you have a, like if I write it this way, like it would be fine with x over 3, like that, leave it in the top. Or I can write it like this, 1/3 times x, because when I write this x like multiplied over to the side, this is like an x over 2 lengths if you multiply back together. So it can look like either one of these, but it cannot be like 1 over 3x. That would be wrong, and it can't be 1x over 3x. That would be wrong. Okay, let me show you what you should get. See if we've got it. The second one you should get positive infinity, negative infinity. For the third one, you should get both of them negative infinity. Okay, questions? Yes. Essentially, you're just subtracting your exponents for that, because what happens is you've got 4 x's on top, and then you've got 3 x's on the bottom, which just leaves you with a single x. So I didn't put the 1 there. You can put it if you want. But pretty much the rule there is you just subtract top minus bottom for the exponents. Okay, now I do want to put a note here. If the degree of the numerator is exactly one more than the degree of the denominator, the function has a slant asymptote, which is kind of like a crazy, a little bit hard to find thing that we will learn more about later, but not in this section of notes. Okay, so just know that like number 2 would have a slant asymptote. Number 1 would have a slant asymptote, and we'll learn about what to do with those later. For that, it doesn't change in behavior; it still goes like to positive or negative infinity. But something to think about. Okay, we are not going to do these calculator instructions because we don't have to use the calculator. So we're not going to do those. But I have the question, what if the degree of the numerator and the denominator are the same? So I am going to use Desmos on this. I should go back, I guess, and put the Desmos. I'm going to walk through that one more time on my Desmos instruction. So if you have this and you're wanting a table, f of x equals 3 minus 6x squared over 2x squared minus 4x. So make sure there. Hold on a second. There's a better way than what I was doing. I forgot about this one. You can do what I did before, but if you hit the gear right here, there is a table button. So you don't even, it automatically does it for you if you do that. So that is a better way to get there. I forgot about that one. So all I did there is I hit the gear. It gave me a table option. I clicked on it right there. Now this puts in automatically -2, -1, 0, 1, 2. Those aren't the numbers we need here, but I'm pretty sure it lets us type in. Yeah, it lets you type in whatever you want to put in there. So you can just type it in like so. Now look at here. We got, I'm getting -0.5, -2.4875, -2.941, ... I'm going to not put the whole thing there. -2.994, ... What does it look like we're getting closer to there? Looks like it's probably -3. If you're unsure, you could put in, some bigger negative numbers, so like negative 10,000. Every time I add a 0, I just get like more 9s, right? Looks like it's getting closer to -3 here.
So like when they're the same exponent, it's actually like instead of going to 0 or infinity, it's an actual number.
Yes. Yep. And we'll see how to find that number here in an easier way just in a second. So, all right. So if I do this for the right-hand side, I've got 1.5, and I've got -3.73, -3.06, -3.006. What's it look like to happen in here? Still to -3. It's from the other side, right? We're coming from numbers below -3 instead of above, but it's still approaching -3. So, if f of x equals ax to the n over bx to the n, notice right here, the key right here, is that those exponents are the same. If the degree of the numerator is the same as the degree of the denominator, as the x values of the function increase without bound, the y values approach a over b. And my shortcut for this is EATS DC. EATS DC stands for exponents are the same. Divide coefficients. Right, so there we've got exponents are the same, divide coefficient. That's our ECC. So Bobo is bigger on bottom, 0. Botno is bigger on top, not 1. That means it'll be positive or negative infinity. And then each DC is exponents are the same, divide coefficients. So you are just looking at, you need to look at the highest degree term. So that would be this and this. If they match, if they are the same, then you are going to divide those coefficients. So I'm going to write it this way. The limit as x approaches negative infinity, I'm going to call it y because it's too long, equals the limit as x approaches infinity of y. I'm putting those two equal to each other because it does not matter if you approach positive or negative infinity. For these types of functions, you're going to get the same answer. So they're going to be equal to each other. And I'm going to do 3 divided by negative 1 to get negative 3 right there. Example 2 is a little bit trickier because it's not expanded yet, right? So if I've got t minus 3 squared, that really means t minus 3 times t minus 3. Now what I want you guys to be able to do for me, whenever I do this, I do it in my head. I do not like write it out the long way because you could do t squared minus 3t minus 3t plus 9. You could do it that way. But I do a square, double, square. It's going to happen the same way every time because you square the first term. These two in the middle are always the same, so you double them and then you square the last term. So I square the first term. T squared is t squared. Then you need to multiply these two together. T times negative 3 is negative 3t. And double it. Double it means to multiply it by 2. So that will give you negative 6t. And then you square the last. So negative 3 squared is positive 9. So I want you to be able to do those in your head if you can. Although I would rather you be slow and correct than fast and wrong. So if you need to write it out, that's fine. And then we got 9 minus 2t squared. So before you can use the ECC shortcut, you have to have everything expanded out. Then you can look at the highest exponents on top and bottom. So here our limit as, be careful right here. I don't need to say x approaches infinity. What needs to approach infinity here? T. T is our independent variable. So it's the limit as t approaches negative infinity of h of t should be the same as the limit as t approaches positive infinity of h of t. And that is going to equal, we're doing positive 1 over negative 2. So we get negative 1/2 for that.
So could you just do it so that you get like t squared? Like you don't have to do the whole thing.
Right. You really don't need the whole thing there. So if you're just kind of thinking about it in your head, you're thinking, oh, when I square that, I'm going to get t squared and do it in your head. That's fine. Okay, questions? So we've taken a long time to go through that because I want you to understand what's happening behind it. But these questions, there's my Botno ECC. I've already written it on the others. We're not going to fill it in right now. Or should we? Maybe. Let's go ahead. Bigger. It's in one spot. On bottom. That O right there is a 0. Bigger. On top. Not 1. Exponents are the same. Divide coefficients. Again, don't use it as your reasoning on the AP exam, but it is very helpful. A lot of these show up where you don't have to explain yourself. You just have to give the answer. So it's very helpful. So we should be able to do these fast, right? So number 1, bigger on top, not 1, but I do have to think about x squared over 3x, which would reduce to 1/3 x. So my limit as x approaches positive infinity of x squared over 3x minus 3. Since I didn't name that, I kind of have to do that. Actually, this one only asks us for negative, so let's... Positive infinity, though, would be positive. What's negative infinity going to be? It will be negative infinity, so that would be your answer right there. Okay, number 2, exponents are the same. Divide coefficients. Be careful for this negative out here. It needs to either go top or bottom, not both places, but top or bottom. So watch out for it. So this one is going to be, there's like a 1 here, so you're doing -2 over 1. You'll get -2. Notice number 4 also has that negative out front. You got to watch out for that. 3. That is Bobo. Bigger on bottom. What do we get for bigger on bottom? 0. Number 4. That's Botno. Bigger on top, right? So if it's bigger on top, I have to do, now be careful. That negative right there, you either need to put it on the top or the bottom. I have a habit of just putting them on the top. So you're doing -1 x to the 3rd over 4x squared, which would be -1/4 x. So it's going to be positive. Our right side would be negative, but it's asking us for the left side, which is going to be the opposite direction for that. Okay. 5 is bigger on top, so we got to do that same thing again. 3x squared over 3x. This is going to give us 1x. The right side would be positive, but they're asking us for the left side, which is going to be negative infinity. And the last one is ECC. Exponents are the same, so we're just going to divide those coefficients right there. 3 divided by 1 is going to give us 3. If you get a number, it does not matter whether you're going to positive or negative infinity. That only matters if you got the Botno situation where it's bigger on top. All right, so, okay. I'm going to do my quizzes at the beginning of classes of warm-up tomorrow, because I got a quizzes for us to practice this a little bit. This stuff is not on your homework, because we were going to do the quizzes for it. But we also only have 17 minutes left. So we'll save this. I've got a quizzes for us to do. We'll do it instead of the warm-up tomorrow, so we get some practice. So your homework, it does not have any of this on it. It's because we were supposed to do the quizzes. But we'll do it tomorrow. Yep. It's not got a lot of questions. I think it's got like 8 questions. All right, so zeros of rational functions. That's the other piece of this that we have to talk about. So this is sort of separate from in behavior sort of stuff. So all that in behavior stuff, we'll do a quizzes to practice it a little bit more tomorrow. We're sort of shifting gears. This is 1-7 and 1-8. I've squished them together, trying to save a little bit of time because otherwise we're never getting through. This is the 1-8 part. Rational functions have zeros, which remind me again, what's a zero? X-intercept. At any value where the blank equals 0, but the blank does not equal 0. Okay? The answer to this is numerator, but the denominator does not equal 0. The reason for that is if I have 0 divided by any other number, let's say 3. What is 0 divided by 3?
0.
It is 0. But if I have 3 divided by 0, that is undefined. And even worse, I don't know why I just said that. And even worse, if I have 0 divided by 0, you guys haven't even learned about this yet, but you will later. That is called the indeterminate form, and you can't do anything with it. Basically, the bottom can't be 0 is all we really need to know right now. So, if I am looking at these functions, I want to factor the whole thing, but only so that I can rule out some answers if I end up having a problem, right? The bottom I only care about because I can't have 0 there. Actually, you really don't have. You could not factor the whole thing. Let's do it both ways. So, like, if I factor the whole thing, I will get x and x here, and I will get a plus 3 and a plus 1. Okay? The numerator is where I get my zeros, right? So if I've got x plus 3 and x plus 1, my zeros theoretically should be x equals -3 and x equals -1. However, if we look at the bottom of this function, this would be x plus 3, x minus 3. They do kind of cancel out right there. So where these two cancel, it's going to cause us to have a hole in the graph. We're going to talk about that more specifically later, but I think we do it some in Math 3. So you've got what we call a discontinuity there. So this one over here that is at, this one is telling us right here, the denominator cannot equal 0. So x cannot equal -3 and x cannot equal +3. The +3 is not an issue because it wasn't a 0 to begin with. But the -3 is an issue. So this one is not actually a 0. You only have one 0 for that one. So the only reason you got to think about the denominator is to rule numbers out. So you can do this by factoring. If you have a term that cancels out, then there's a hole there and you're not going to have a 0 at that point. So you can do it by factoring. The other option you have here, we got something we got to factor here. This is some of that trickier factoring that we have. It doesn't go away. You have to know how to do it. So 3x squared will have a 3x and an x. I've got a 4 over here, and I know I'm going to have to use negatives or else I would never get a -7 in the middle. So I could either do -2 and -2, or I could do -1 and -4. Okay? And if you think about playing around with what's going to work there, 2 and 2 is not going to work because that would give me like -8. If I do -1 here, no, wrong spot. -4 here and -1 here. That is going to work because this would be -4x and this would be -3x, and that would give me -7x, which is what I want. All right. So since I have factored that numerator there, I could set each one of those equal to 0. The second one is easy. I get x equals 1. The first one's a little trickier because it's not just going to be 4 for that one. I've got to do 3x minus 4 equals 0. That would give me 3x equals 4. And then I would divide by 3. So I would get x equals 4/3. And then think about plugging those numbers into the bottom to make sure you don't also get 0. So if I plugged in 1, I would get 2 minus 5. That's not 0, so it's fine. I'm not 100% sure about 4/3, but I'm pretty sure that's not giving me 0 either right there. Or your other option is factor that denominator. That factors into x times 2x minus 5 right there. Nothing cancels. So these both are zeros right here. So for zeros, you only care about the numerator, but you got to use the denominator to make sure there's not a hole there. Yeah. But like you don't get a x equals 3 is not a 0 right here. Does that make sense? Okay, so rational inequalities. This is very similar to the polynomial inequalities that we did. In fact, very, very similar. You're going to do it very much the same. So, you are, if it's not already, moved everything to one side. You need to move everything to one side. I don't think you're going to see any on your homework that are like that. Yeah. Then, you will factor everything if it's not factored. A lot of the ones you're going to see are going to be factored. I think everything you're going to see is going to be already moved to one side. This one's already factored for us. So we need to find the zeros and the excluded values. Okay? So the zeros come from the top. We would get our zeros would be x equals 0, x equals 1, and x equals -2. My excluded values come from the bottom. And in this case, it's x cannot equal 5. Okay, because we can't have a 0 in that denominator. But whether it's zeros or excluded values, you're still going to put them on your sign chart. We're going to do a sign chart just like we did for the polynomials. So, I'm going to have -2, 0, 1, and 5 right here. And then I'm going to take each piece, each factor of this function, top and bottom. It doesn't matter if it's top or bottom. You're using all of them. And I'm going to put them over here on the side. So I would have -2x squared, x minus 1, x plus 2, x minus 5, and like we did with our polynomials, let's put us a line for our answer. And then you're going to draw in the chart here. And then, just like we did with polynomials, we're filling in positives and negatives. So for this top term, you've got an x squared. When you square something, it's always positive. But if you take that and then multiply it by -2, it is always negative. So that whole top line should be negative. On the next line, we've got x minus 1. So, you're going through thinking of the numbers. If I plug in something like -3, I would still get a negative. Really, I'm going to get a negative all the way up until I get to 1, which would make this 0, right? And then anything bigger than 1, so like 2 and beyond, that would give me a positive for that line. Do the same thing with my 2. I'm going to get a negative here. X plus 2, like if I plug in a -1, now I start to get positives, and that's going to carry across for all of these. And then my x minus 5 is going to be negative all the way up to the 5. And if I plug in something bigger than 5, like a 6, I'll get a positive. And to do your answer line here, you would just look at your columns. You have 4 negatives here, which is going to give you a positive overall. It doesn't matter whether the numbers are being multiplied or divided because the rules for multiplying and dividing are the same, right? So like, yes, we are doing negative times negative times negative divided by a negative here, but the rules are going to be the same. If you have an even number, you're going to get a positive right here. This will be negative. This one will be negative. We get a positive here and a negative here. Okay, there. Okay, which ones are my answers, the positives or the negatives? Negatives, because I had less than 0, so negatives. Now, a couple things that we have to keep in mind. 5 is an excluded value. It cannot be 5. So we cannot use a bracket at 5. Do we need to use brackets anyway? We do not, because we don't have an or equal to sign right here. So it's not an issue on this problem because we're not using brackets, but it could be an issue on a different problem that had an or equal to with it. So you can use the number 5, you just can't put a bracket with it. Also, because when you put parentheses with it, it means you're going all the way up to 5, but you're not including 5. So you've got 4.9, 4.99, 4.99999, 4 gazillion nines, but not 5. When you put the bracket is when it includes 5 for that. So you're going to do -2 to 0, 0 to 1, and 5 to infinity.
You not do -2 to 1?
You cannot on this one, and this was something a few of you did on the test as well. You cannot do -2 to 1 on this one because we have a less than sign. And at 0, our function equals 0. Right? So that is not less than 0. It's equal to. If there were a or equal to sign, we could combine those two. But at 0, we can't include that. So if you see, like, on your test that says not at x equals 2 or something like that on, like, graph question, you need to break that up into 2 separate sections for that there. Okay, questions? It's very similar to the polynomial stuff. You just got a denominator here. We don't have time to do this one. But let me just do the first step right here. If it's not factored for you, you need to factor it. So you would have 2x and x, and then I think we could do a +7 here and a -1 here, right? And then the bottom would be 3 minus x. You can check that by going over here. That'll give you your -1x. That'll give you your +14. Put them together, you get 13x right there. So the zeros for this, zeros would be x equals -7, 7 right there. And then the 2x minus 1, I'd have to do 2x minus 1 equals 0. So that'd be 2x equals 1. I divide by 2. So x would equal 1/2. My excluded value would be x cannot equal 3 right there. It's backwards, but 3 minus x equals 0. You just add the x, and 3 would equal x right there. And so you would put those on the number line, use the factored version of it to do the problem for that. Okay? So let me stop that here.